Download this code from codegive.com, link in the description below. OK, let's dive into the world of perceptrons. This guide will provide a comprehensive overview of perceptron neural networks, covering their theory, implementation, limitations, and practical applications. We'll include a code example in Python to solidify your understanding. What is a perceptron? A perceptron is the fundamental building block of many artificial neural networks. It's a simple, single-layer neural network used for binary classification tasks. Essentially, it takes a set of inputs, multiplies them by corresponding weights, sums the weighted inputs, adds a bias, and then applies an activation function to produce an output. The output is a binary value, typically 0 or 1, representing the class to which the input belongs. Core components of a perceptron. 1. Inputs, x_1/sub, x_2/sub, xsubn/sub. These are the features or attributes of the input data. Each input is a numerical value. 2. Weights, w_1/sub, w_2/sub, w_n/sub. Each input has an associated weight. These weights represent the importance of each input feature in determining the output. The model learns the optimal weights during the training process. 3. Bias, b. The bias is an additional constant added to the weighted sum of inputs. It allows the perceptron to make predictions even when all inputs are 0. Think of it as a shift that can activate the perceptron even when no inputs are provided. 4. Weighted sum *, the sum of the inputs multiplied by their corresponding weights, plus the bias. Z equals, w_1/sub x_1/sub, plus, w_2/sub x_2/sub, plus, w_n/sub x_n/sub, plus b. This can be written more concisely using vector notation. Z equals w_t/sub x plus b, where w and x are vectors and w_t/sub is the transpose of w. 5. Activation function, phi. The activation function introduces nonlinearity into the model. It takes the weighted sum, z, as input and produces the output of the perceptron. In the classical perceptron, the most common activation function is the step function. Asterisk step function, Heaviside step function. Asterisk phi, z, equals 1 if z equals 0. Asterisk phi, z, equals 0 if z 0. Other activation functions can be used, but the step function is the canonical choice for perceptrons. 6. Output, y. The final output of the perceptron is the result of applying the activation function to the weighted sum. Y equals phi, z. The perceptron learning rule. The goal of training a perceptron is to find the optimal weights and bias that allow it to correctly classify the training data. This is done using the perceptron learning rule, an iterative algorithm that adjusts the weights and bias based on the prediction errors. Here's how it works. 1. Initialization *, initialize the weights and bias to small random values or to 0. 2. Iteration * for each training example, x, y. A forward pass * calculate the predicted output y using the current weights and bias, y equals phi, w_t/sub x plus b. B. Error calculation * calculate the error e between the predicted output y and the true label y, e equals y, y. C. Weight and bias update * update the weights and bias based on the error. W_i/sub equals W_i/sub plus eta *e x_i/sub, for each weight W_i/sub. B equals b plus eta *e, where eta, eta, is the learning rate. The learning rate controls the step size of the weight and bias updates. A smaller learning rate leads to slower but potentially more accurate convergence, while a larger learning rate can lead to faster convergence but may overshoot the optimal solution. 3. Repeat step 2 for a fixed number of iterations, epochs, or until the error on the training data reaches an acceptable threshold, i.e., the perceptron classifies most or all of the data correctly. Geometric interpretation. The perceptron essentially learns a linear decision boundary, a hyperplane in higher dimensions, that separates the two classes. The weights and bias define the orientation and position of this hyperplane. Data points on one side of the hyperplane are classified as one class, and data points on the other side are classified as the other class. Python code example. Explanation of the code ***. 1. Perceptron class ** encapsulates the perceptron's functionality. *__init___ self, learning _rate equals 0.01, n_iteers equals 100, the constructor. It initializes the learning rate, number of iterations, weights, initially none, and bias, initially none. Step _function, self, z, implements the step function. Returns 1 if z is greater than or equal to 0, and 0 otherwise. Fit, self, x, y, the training function. Takes the input data x and labels y as input. Initializes the weights to a vector of zeros with the same length as the number of features in the input data. The bias is initialized to 0. Iterates n_iteers times, the training loop. In each iteration, it iterates through each training example in the dataset. For each training example, it calculates the weighted sum of the inputs and adds the bias. It then applies the step function to the weighted sum to get the predicted output. It calculates the error between the predicted output and the true label. Finally, it updates the weights and bias based on the error and the learning rate. Predict, self, x, the prediction function. Takes the input data x as input. Calculates the weighted sum of the inputs and adds the bias for each example. Applies the step function to each weighted sum to get the predicted output for each example. Returns the array of predicted outputs. 2. Example usage, if __name ___ equals __main __:. Sample data creates sample data for the n and or gate functions. The X array represents the input features, 2 binary inputs, and the Y array represents the corresponding output, 0 or 1. Create and train creates a perceptron object with a specified learning rate and number of iterations. Then, it calls the fit method to train the perceptron on the sample data. Make predictions calls the predict method to make predictions on the same sample data. Print results prints the predictions and the accuracy of the model. How to run the code *. 1. Install NumPy *. If you don't have NumPy installed, install it using pip install numpy. 2. Save the code *. Save the code as a Python file, example perceptron.py. 3. Run from the terminal *. Open a terminal or command prompt, navigate to the directory where you saved the file, and run the code using Python perceptron.py. Output *. The output will show the predicted outputs for the n and or gate training data and the accuracy of the trained perceptron. You should see predictions that closely match the truth tables. Limitations of perceptrons. While perceptrons are a valuable starting point for understanding neural networks, they have significant limitations. 1. Linear separability *. Perceptrons can only learn linearly separable data. This means that the data must be able to be divided into two classes by a straight line, in 2D, or a hyperplane, in higher dimensions. If the data is not linearly separable, the perceptron will not converge to a solution. A classic example of a nonlinearly separable problem is the XOR gate. Two binary classification only * standard perceptrons are designed for binary classification, two classes. While variations exist for multi-class classification, they are not as straightforward as other neural network architectures. 3 No hidden layers * perceptrons are single-layer networks. They lack the ability to learn complex patterns and representations that require multiple layers of processing. Overcoming the limitations, multi-layer perceptrons, MLPs. The limitations of perceptrons can be overcome by using multi-layer perceptrons, MLPs. MLPs have one or more hidden layers between the input and output layers. These hidden layers allow the network to learn nonlinear relationships in the data and handle more complex classification and regression tasks. MLPs are significantly more powerful than single-layer perceptrons and are the foundation for many modern deep learning models. Applications of perceptrons, and related concepts. Despite their limitations, the concepts behind perceptrons are foundational and have applications in simple pattern recognition * in situations where the data is linearly separable, a perceptron can be used for basic pattern recognition tasks. Feature selection * the weights learned by a perceptron can provide insights into the importance of different features in the input data. Features with larger weights are generally considered more important. Building blocks for more complex networks * the perceptron serves as a fundamental component in more complex neural network architectures like MLPs and convolutional neural networks, CNNs. Understanding neural network fundamentals * studying the perceptron is an excellent way to learn about the core principles of neural networks, such as weights, biases, activation functions, and the learning process. Control systems * in some basic control systems, a simple perceptron-like model can be used to make binary decisions based on sensor inputs. Key takeaways. The perceptron is a simple, single-layer neural network for binary classification. It learns a linear decision boundary to separate the two classes. The perceptron learning rule is used to adjust the weights and bias based on prediction errors. Perceptrons are limited to linearly separable data and binary classification. Multi-layer perceptrons, MLPs, overcome these limitations by adding hidden layers. The perceptron is a foundational concept in neural networks and is useful for understanding more complex architectures. This comprehensive guide should give you a solid understanding of perceptrons. Remember to experiment with the code, try different data sets, and explore the limitations firsthand. Good luck.